Hey there, AAF students. Welcome back. In this lesson, we're going to extend on our understanding of linear combinations that we know about solving 2x2 systems, right? So 2 variables, 2 equations in order to successfully solve and describe, right? That was a new thing that we learned in our last lesson. A 3x3 system, right? So a 3x3 system, really here we're working with planes, right? So you're going to have 3 variables and 3 equations. 3 variables, 3 equations. All to the degree or with an exponent of 1, right? So we're using linear combinations, which was the add, down, or the elimination method here. It's obviously going to be a little bit more involved. There will be some substitution that we're using, but we are doing this with that method of elimination, where you're trying to get rid of a variable, or in this case, obviously we are going to be trying to get rid of 2 variables. So we're really extending on what we did. So with that being said, I would really encourage you to either have this PowerPoint printed out or your notebooks out so that you are able to follow along. So before we get too far into this, I want to look at describing, just to make sure that we have this with 2x2 systems before we build and get to 3x3. So determine the type of linear system. So notice it doesn't say solve. So this should ideally be a pretty quick thing that we're doing, right? We don't need to go too far into this. We just want to see what happens. Like, we really want to look at it so that we know what the end result will be, because I just have to figure out what type of system is it. Is it independent consistent? Is it dependent consistent? Or is it inconsistent? So I'm going to start by rearranging this. So I've got 2x minus 6y equals negative 10. And then I've got x, nope, I guess that's going to be negative x minus 3y equals 5. So if I look at this right now, I could attempt to solve this, but why don't we look at like what would happen if I was trying to do the elimination method here, the linear combinations. I would probably multiply through by 2, right? Watch what happens if I multiply through by like negative 2 though, right? So I would get 2x plus 6y equals, am I doing that right? Negative x minus 3y. And then negative 10. Negative x minus 3y. Right, so my variable here, I have the same coefficient. Here and here, oh, it's not the same coefficient. Here it is, right? So I would get a solution, like I would get a value for y. I'm going to, like when I add down here, like something's going to cancel, but something else will stay. So I can just look at that piece of it and realize that they have different slopes, right? Automatically, when they have different slopes, like this has a slope right here. Remember, if you have negative a over b, think standard form, link it back to that. You have 1/3. This is going to be a negative x over here. Negative x minus 3y equals 5, right? That's what I have there. If I do negative a over b, I'm going to get negative 1/3. They're going to intersect, right? So this is going to be independent, consistent. It doesn't ask me to actually solve it, right? I don't need to take the time to continue to solve it. I just want to think about like what would happen. Let's look at this next one. So let's do the same thing. So these are already in standard form. So let's look at we can look at their slopes, right? So this is going to give me a slope of negative a over b is going to be 4 over 7. Negative a over b here is also going to be 4 over 7. So it's the same slope, right? So I just have to figure out, well, are they going to intersect? I'm sorry, are they going to be the same line? Or are they going to be parallel lines? And so then I can take a look right here. Well, they have a different constant, right? These are just going to be parallel lines. That means they're going to have a different y-intercept. So these are going to be parallel. So how would we describe that type of system? inconsistent. Right? That is an inconsistent system. They have no solutions. There is no unique solution here. Right? Like there's no point that they intersect. There's no line that they intersect at. And finally, in this last one, let's take a look at this as well. So let's look at their slopes. Negative a over b is going to give me negative 4/3. Negative a over b is going to give me negative 4/3. Right, so here I would have to, yeah. So when I go ahead and if I were to solve, so let's say I were to just take this to make it look like the one above, let me multiply by -2 so then I can see these, right? So maybe I should have actually back here multiplied by -2 and I would have seen it's -8x plus 14y equals 6. And I have a 6 and a 5. So this didn't actually impact me that much. I probably want to look at it when I dilate it. So -8x minus 6y equals -14. Well, I have a -14 and a 15. They have different constants in the same slope. So these, again, will be parallel lines, which means that they are inconsistent. So there is no unique solution, right? There's only a unique solution if you have a point of intersection. Right? Whereas you have an infinite number of solutions if they're the same line. Pretty neat. Okay. So just to, again, like refresh on this before we get too far into talk, or before we begin talking about 3x3, if it's independent consistent, and these are the terms that we've got to know as far as when you're asked to describe or classify, could be another way that you are told to do this, like classify the system. Independent consistent, that means that there is one unique solution, right? And your answer will be a point. Like, what is the point of intersection? If it is dependent consistent, this means that there is no unique solution. You will have an infinite number of solutions. Right? They're the same line. So your solution will be the equation of a line, of the line that they are. They're the same line. Right? So maybe it looks like y equals mx plus b for a 2x2 system. Right? This would be xy for a 2x2 system. If it is inconsistent, this means that we have parallel lines. Right? And again, there is no unique solution here. There is really no solution. Right? Or no solution. So when you got down to this, and this is something where, like, when it cancels out, right, if you're doing the elimination method or the add down or linear combinations, you can get something that's like 0 equals 8, and you're like, that is nonsense. Right? Whereas here, you're going to get something like 0 equals 0, and you're like, that's true. Right? So that's what this could look like. That's what this could look like. And for this one, you would say something like the empty set would be your solution. Right? There is none. There is no point or line of intersection. So we're not going to get quite as in-depth with our description of systems when we talk about 3x3, because as you get later on into, this course and pre-calculus and just as you move forward, linear algebra, you'll learn more about how to classify, but we need a little bit more information when we're dealing with 3x3. So we're really going to be talking about, like, is there a point of intersection for 3x3? Is there one point they intersect at? Or not, right? So I'm really going to go with, like, it is independent consistent, like it's an independent system, or there is no unique solution. So the reason behind that is like when we're dealing with a 3x3 system, it's planes. And I don't know if you guys recall, this is not going to be a pretty picture, but if I'm looking at planes intersecting, they're going to intersect. I don't know how to get this to look right. Oh no, no. It doesn't look good. They could intersect at a point. They could intersect at a line. You could have two that intersect. right? They don't, all three of them don't have to intersect. Two of them could be parallel and the other one could go through both, right? So it's like, is it skewed or is it like that idea? So we're really going to go here with like, is there one unique solution or no unique? So it's either independent consistent or no unique solution. So you don't have to worry, at least for the right now. We'll build to get there later. You don't have to worry about, well, if there is no unique solution, does that mean that none of them ever intersect, or do they intersect at a line, or what happens? So for this first one, we're going to go through 4 examples. So solve the 3x3 system using linear combinations, identify the type of system. And as I said in the last video, make sure that you are getting in the habit of always identifying, right? So like that's what, even though the textbook didn't say to do it, when you had your last homework assignment in the textbook, we asked that you still identified, because that is an important piece of this. So what I'm going to do here is I like to letter them. I could number them too. I'm going to say this is A, this is B, and this is C. And there might be cases in which you can eliminate 2 variables at once, and that's nice, but that won't always happen. So I'm going to pick 2 of these, and I'm going to pick a variable to eliminate. So you can pick something different than what I'm picking. What I like to do is actually number my steps to keep it organized. That helps us to be able to follow your work as well. And then if you get lost in something, that helps you backtrack and like back map to see like, well, where did I go wrong? Or if you're looking back at your work, you're like, what did I do here? So I like to number my steps. So the first thing that I'm going to do, and I'm just going to pick A and B. So I'm going to use A and B. And I'm going to eliminate Z. That's going to be my goal, right? So have a purpose behind what you're doing. So I've got 3x plus 2y minus z equals 4. And 5x minus 3y plus 2z equals 1. I'm going to have to multiply this first one by something. I'm going to multiply it by 2, because remember my goal going into this was to get rid of z. So I'm going to have 6x plus 4y minus 2z, so you can kind of see maybe why I did that, equals 8. And I'm going to add down. That's going to give me 11x. This will give me just y. Those are going to cancel. That was my purpose, equals 9. I'm going to hold on to that. I'm going to star it so I don't forget about it. I'm now going to go to step 2 for mine. I'm going to pick 2 other equations. So when I'm saying 2 others, I need to pick C. C and something else. I don't care which other one you pick, but I need to use the third one. And I need to, my goal is to eliminate the same variable, Z, right? So then I will have a 2x2 system, if you can kind of picture where I'm going with that. So I'm going to choose to use C and B. It's just, if you're setting it up differently, if you're solving for a different variable first, that's fine. I think Z might have been the most logical, because if you can see, they're all factors of 8. Whereas if I was going to go for Y, it might not eliminate as nicely, or X might not eliminate as nicely. So I'm just going to choose C and B, so I'll rewrite B. And then this is 9x minus 13y plus 8z equals negative 5. I'm going to take the first one, and I'll multiply through by negative 4. I could also just multiply through by 4 and then subtract the 2. That works too. So it'll give me negative 20x plus 12y minus 8z equals negative 4. So just be careful when you're doing this. And I'm going to add down. 9 minus 20 is going to give me, what is that? Negative 11x. Negative 13 plus 12 is going to give me negative y. That goes away. That was my purpose. Equals to negative 9. So now I've got 2 equations with just x and y, right? I've eliminated z. So I'm going to take those in step 3. I'm going to pull those 2. Negative 11x minus y equals negative 9. And 11x plus y equals 9. When I go to add down, right, I don't need to multiply through by anything, but if I did, that's where I would go with this. That cancels, that cancels, that cancels. I get 0 equals 0. Everything just canceled. Well, what does this mean? This means that I have no unique solution. I want to make it clear that if I did something here and I didn't get 0 equals 0, I might need to go back and look at my work. So what would be really good is if you did this a different way, right? If you were like, I already know how to do 3x3 systems and you tried it, that you take a look at your work and see, like, does your work actually make sense? Like, did what you do make sense? And if you're not sure, share it with us. Let's look at another one. Let's see, example 2 here. So I'm gonna go about the same exact process in a new color because I would like to use red. So step 1. Oh, I'm gonna name them A, B, and C so that I know what I'm talking about, and this makes it a lot easier for us to see it too. I'm gonna go into this thinking about, I'm gonna try to get rid of X, right? I think to me, when I'm looking at X, that's going to be the most simple one for me to get rid of. So I'm going to start with A and C because I don't think I'm going to have to do any multiplication. See how nice that's going to be? X plus 3y minus 3z equals 12. Negative x plus 2y minus z equals 1. And I'll go ahead and add down. X's go away. 5y. Negative 3 plus negative 1 is negative 4z equals 13. Okay. Star this, know that I'm going to need to be using it. So I'm still going to be trying to get rid of X, but I need to use B in it. So I'm going to choose to use B and C. It doesn't really matter. So negative X plus 2y minus Z equals 1. Oh, I don't know why I wrote C first. It doesn't ultimately matter. Plus 4Z equals 0. I'm going to multiply through by 3. I like to write it before I multiply because I think, again, the more I show my process, the more if I make an error, it helps me to identify where my error is because mistakes happen. And then it helps me if I ever go back and look at my work to understand what I was doing. So add down, my purpose was to get rid of X. Negative y plus 6y is going to be 5y. 4 plus negative 3 is plus z equals 3. Okay. So now in my next step, just like I did before, I'm going to put those two that I starred together. And let's see what we can get rid of. Do we need to multiply through by anything? Oh, what does it look like I can get rid of pretty quickly here? Y. I'll just subtract. Those go away. Z minus negative 4z is 5z. 3 minus 13 is negative 10. Divide by 5, divide by 5, z equals negative 2. So now that I've got negative 2, I know that there's going to be a unique solution, right? I just got a z. So I need to now work to find the other one. So I'm going to put up here what's x, what's y, what's z at the top here. And then as I get them, I'll write them down so I don't get lost in my work. So let's go back up here to step number 4. So I'm going to go ahead and I'm going to find y now. I'm not going to do, I could do more linear combinations and try to get rid of something else, but what's the point, right? Like I could plug in z to 2 of these and do something with linear combinations, but I think I'm just going to go back up here to the one that I starred and substitute in. 5y minus 2 equals 3, right? So in the place of z, I put a negative 2. 5y equals, add 2, 5, y equals 1. Oh, I've got a y now. 1. Now I've got a y and a z. I'm going to go back to one of my original ones and plug those in. I'm going to choose to do it in A, just because it looks like one that I might want to use, right? Because x is already by itself, but it doesn't matter. X plus 3 times 1 minus 3 times negative 2 equals 12. You can choose to do a different one. If you thought C looked nicer to do it because it was smaller numbers, that's fine, right? Because realistically, we shouldn't be using a calculator right now. X plus 9 equals 12, so x equals 12 minus 9 gives us 3. So I got my x, my y, and my z. So I have a unique solution. I have a point where these three planes intersect. So this is independent, consistent. Like there is a point that these three intersect at. A single point. So let's see. Should write this out just as we did with a 2 by 2. 3, 1, -2. Amazing. So you saw one where things canceled and there was no unique solution, or you've got one solution. Okay, so let's see here. Solve the 3 by 3 system. I would say this is a great time if you haven't paused the video that you maybe want to try one on your own. Do it. Let's see. A, B, C. My step 1. I'm going to use B and C. I'm going to try to get rid of Z. I think that's my nicest one to get rid of, in my opinion. And I'm going to do B and C. So 2x plus y plus 3z equals 3, and 6x plus 3y minus 3z equals 37. I'm going to go ahead and add them because that will get rid of my z's. I'm just going to cross them out. 8x plus 4y equals 40. Could probably simplify that if I wanted, right? Probably divide everything by 4. Let's do it. Divide everything by 4. 2x plus y equals 10. That's nicer. And then I'll write them both and see which one I need in a moment. Okay, so for step 2, I'm going to have to use A, and I'll use something else. I'll use A and C. And I'm going to take C and write that here. Oh, yeah, I'll do that. It's fine. Maybe, yeah, it's fine. They're both bigger numbers, so it's fine. 4x plus 2y minus 6z equals 34. And I'm going to multiply this one by 2. 12x plus 6y minus 6z equals 74. And I'm trying to get rid of these, so I'm going to subtract. Those go away. 4 minus 12 is going to be negative 8x. 2 minus 6 is going to be negative 4y. Equals 34 minus 74 is 40. Right? No, negative 40. So I'm going to do the same thing. I'm going to divide everything by negative 4. And I'm going to get 2x plus y equals 10. So let's see. What happens here when I take these two in step 3? 2x plus y equals 10. I guess I didn't need to do that. I would see it regardless. And 2x plus y equals 10. They're the same. It all cancels. And I get 0 equals 0. So what does this mean? There is no unique solution. Amazing. Okay, we're going to do one more. Example 4. One more. So solve the 3 by 3 system using linear combinations and identify the type of system. Oh, this looks weird though, right? I've got 3, but there's only 2 variables in each. So what does that mean? This must be 0x plus 3y plus 4z equals 6. This must be 3x plus 0y minus 5z equals 3. 2x plus 5y plus 0z equals 2. Huh. Got A, B, and C. We're going to go about it the same way, but let's see what happens. This one's kind of cool. I think they're all cool, but I think this one's exceptionally neat. So my goal, I'm going to try to get rid of X. So I'm going to use B and C. I just thought those were nice numbers to multiply through by. So if I've got 3x plus 0y minus 5z, I like to write in that so I don't get confused when you're lining things up. I like for it to line up nicely. So for something like this, I'm going to actually have to multiply both of them, right? I'm going to have to multiply this by 2 and this by 3. And that's going to give me 6x plus 0y minus 10z equals 6 for the first one. And 6x, so that was my goal, plus 15y plus 0z equals 6. And I'm going to go ahead and subtract. Bye. 0 minus 15 gives me negative 15y. Negative 10 minus 0 gives me negative 10z equals 0. So let's see. So what's neat about this is since there's only 2 variables in each one of these original ones that I'm given, I'm going to choose to just go the route of substitution now. So I'm going to take what I have, this negative 15y minus 10z. And so this is where like the practice is what's really going to benefit you, right? Like the more you practice, the more you'll be able to look at it and be like, well, what should I do with this? And I'm going to choose to solve for y, okay? So I'm going to divide by 15, and that was a choice. I had many choices that I could have made, but this was my choice. So negative 10 over 15 is negative 2/3 z equals y. In my next step, where I'm going to go with this is I'm going to plug this back in to something that has y and z, right? Oh, look, I'm going to plug it back into A, y and z. So in the place of y, I'm going to do 3 times negative 2/3 z plus 4z equals 6, right? So then I only have one variable. Negative 2z, they cancel, multiply by 3 and divide by 3, plus 4z equals 6. This is going to give me 2z equals 6, so z equals 3. And so I'm going to go up here and say what's x, what's y, what's z. Z is 3? Yeah. Okay, now I've got z. Well, I'm gonna go for this. In my next step, I have z. I'm gonna use b, and I could do anything right now, but I'm gonna try to get x. Right? I've got 3x minus 5 times 3 equals 3. Right? I don't need to keep doing linear combinations. I started with linear combinations. That's what this told me to do. Go ahead and add 15, and you get 3x equals 18. So x equals 6. Is that right? Three x. Did I do this all right? Negative 2 plus 4. Yes, I'm good. So I've got x equals 6. And then in my fifth step, I need y, so I'll go to c. I'll use c. And I've got 2 times x plus 5y equals 2. 12 plus 5y equals 2. Subtract 12. 5y equals negative 10. So is y negative 2? Right? So like had I taken z right here and plugged it in, 3, I would have gotten 3y equals negative 6. 12, 6 minus 12 is negative 6. And oh, look, I still would have gotten negative 10. So my solution is 6, negative 2, 3, x, y, z. And this is an independent system. So we're not going quite, it's not as nice, or the algebra doesn't as nicely show us if it's inconsistent or if it's dependent consistent. Like it doesn't show us as nicely for this. So we're either saying that there is one unique solution shown by x, y, z, independent, consistent, or saying no unique solution for a 3x3 system. So in this lesson, we extended on what we knew about linear combinations, right? And we also brought in substitution in order to successfully solve and describe a system of 3x3 systems. So I would really encourage you guys to practice. You have a little like post-lesson check-in that incorporates both 3x3 and 2x2, and go ahead and do that. And we will actually be going through that in class the next time that we see you guys, which is the next live session. So please write down any questions that you have, and we will be happy to address them during class or any other time to help you to better understand this. Thanks, everyone. We will see you next time.